In this video, we're going to look at an equation in fluid dynamics known as the Poiseuille equation. And this equation will describe laminar flow through a pipe, and the pipe has to be a lot longer than it is thick. So it's not going to work for short pipes. It won't really describe the flow at the very start or the very end, but it's great for in between. Anyway, a really useful equation, but before we reveal what it is, we're going to have a general discussion about fluid flows. And to discuss fluid flows, we're going to use an analogy. People. Imagine you're a person in somewhere really busy, like an underground subway at a train station. And we're going to model our underground subway as a big, long, rectangular kind of corridor thing. And we've got all these people in our subway trying to get from A to B. Now, really busy, peak hour, we want as many people to get from A to B as they can. So we're going to count the number of people who arrive at the B end of the subway per second. And yeah, really busy peak hour, so we've got an infinite number of people waiting at A to get through the subway and come out at B. They're just going to keep coming. And we're going to call this rate of how many people pass B, we're going to call that Q. Now, let's compare some different subways. Everything about these subways is the same, except that one is a lot wider than the other. Which one is going to enable more people to get past point B? The wider one, of course, because more people can walk side by side. And we'll call the width of this subway D. So, quick recap. The wider the subway is, the more people pass B. As D increases, Q increases too. And we can say that Q is proportional to D. Just for fun, let's imagine that our subway had some height as well as width. And it was as high as it is wide. And people can also walk on top of each other in this imaginary situation. And when they're walking on top of each other like this, you can see that that number of people passing B is just going to get bigger again. Because you've got layers of people just passing B all the time. Much better than a flat subway. And so Q is proportional to the height and the width of the subway. And since these things are both the same, we say that Q is proportional to D times D, or D squared. Where we're up to, Q is proportional to D squared. Let's pretend the subway goes from work to home. It's peak hour, after all, people are going home. And when people are at work, they're feeling stressed, they're working hard. When they're at home, they're really chilled out, relaxed. At work, they're under a lot of pressure. At home, they're under no pressure at all. And so the more pressure they're under at work, the more motivated they are to go home quickly. And the more people will exit the subway. However, we can also imagine a slightly different situation where people really enjoy their jobs. They have a lot of fun at work. And so they don't really want to leave work just as badly. There's not really that big pressure difference between work and home because they're happy in both places. If there's not much difference between work and home, the number of people walking past B will decrease. Big pressure difference, a lot more people walking past B. And remember, we're describing the number of people passing point B as Q. So we've got Q is proportional to the height and width of the subway, and Q is also proportional to the pressure difference between the two ends of the subway. And we use delta P to represent the pressure difference. P for pressure, and delta, which is a Greek letter that we use when we're talking about the difference of something. Up until this point, we've assumed that everyone who's in our subway is walking in the same direction, nice and orderly. But the reality is that people are going to stop and check their phones. People might realise they're going to walk out the wrong exit, so they'll turn around and try and go back. And now imagine if the subway was really long and you've got people who are nearly at the end of the subway and then they realise they've gone the wrong way. So they turn around and they have to walk all the way back along the subway. That's going to be pretty difficult. In fact, you'd say the problem is worse the longer the subway gets. And this problem is in fact what's known as viscosity. We've got a rough model for what viscosity is here. How big is this viscosity effect? Well, it depends on the viscosity of the people, which we'll call mu, Greek letter that looks like this. And it's going to depend on the length of the subway, L, the distance between A and B. And the bigger this gets, mu times L, the fewer people are going to walk past B, the smaller Q is. So there's nothing you can do to sort of take away viscosity, but you can reduce its overall effect. If our subway is both tall and wide, then those people who are stopping to talk on their phones or turning around and going a different way, they can move to the edges. And so everyone else can just storm through down the middle. So we have that for the overall effect of the viscosity, it depends on the viscosity of the people and the length of the subway. But if you have a pipe that's higher and wider, then you've got a larger space in the middle for people to walk quickly when the people who have stopped go to the edges. So the overall viscosity effect decreases the bigger your pipe is, the bigger D times D is. But of course, we care about the overall viscosity effect. As the overall viscosity effect goes up, the number of people exiting the subway will go down. So we say that Q is inversely proportional to the overall viscosity effect. So we've got that Q is proportional to 1 on mu times L all divided by D squared. That's the same as Q is proportional to D squared divided by mu times L. And this is in addition to what we already found, which was that Q is proportional to D squared times delta P. Putting this all together, we get that the number of people exiting the subway per unit time is proportional to the height times the width times the height times the width of the subway, the pressure difference between the ends of the subway, the viscosity of the people on the bottom, and also the length of the subway on the bottom. And while we've had this discussion about people and you're like, what's this got to do with fluid mechanics? Well, it turns out that you can model people as a fluid, like they follow the same equations. People in a subway, crowds, people trying to get through a door, they all behave like fluids do. And so this is why we've ended up being really close to what Poiseuille's equation actually is. Let's write that down. All that changes is that we've added a factor of pi divided by 8, which comes from the geometry of our subway or our pipe. So that's if it's a circular subway or a circular pipe. So here we've got all the quantities that go into that equation. Q, the volume flow rate, measured in meters cubed per second. D is the diameter of the pipe in meters. L is the length of the pipe, also in meters. Viscosity of the pipe is in Pascal seconds. And delta P is the pressure difference between the ends of the pipe in pascals. What's a Pascal, I hear you say? That's 1 kilogram per meter per second squared. 1 Pascal is also equal to 0.0075 millimeters of mercury, which is another unit for pressure. And there you go. That's some fluid dynamics for you, starting with just thinking about people going through a subway.